Hello everyone, my name is Dawid Rymarczyk, and during this presentation I would like to present our work about comparison of supervised and self-supervised deep representations trained on histological images. It is a joint project between RDGen and Jagiellonian University with Adriana Borowa, Anna Bracha, Maurycy Chronowski, Wojciech Ozimek and Bartosz Zieliński as main investigators. In a few slides, I will present the motivation of this work, applied methodology, conducted experiments, obtained results, conclusions, and future research directions. Recently, deep learning methods are applied in many domains, especially in medical imaging. They require a lot of labeled data to train a complex prediction model. However, the labeling process is laborious, expensive, and often requires a highly trained expert. That is why recently introduced self-supervised methods gain popularity. They reduce the need for high amount of labeled data to train a model, maintaining its high effectiveness. Supervised learning assumes that we have an image and a corresponding label. Then the model can be trained iteratively by comparing predictions to desired labels and adjusting model parameters to reduce the disagreement between predictions and labels. However, in the self-supervised paradigm, we do not have a label for each data point. Therefore, in the case of images, we assume that an image after two different transformations is still preserved the key information. To learn a model in such a scenario, we generate deep representations of images after two different augmentations and optimize the model to have the smallest difference between them as possible. After the representation network is learned, we only learn a classifier part of the model only on 5% of the original dataset to have a meaningful model. In our scenario, we use the simpler model, which exploits projection heads on the representations to remove the bias towards image transformations. In the case of deep learning applications, the end users complain about the lack of model's transparency and explainability. They do not understand what are the rationale behind the prediction and find it hard to trust them. Additionally, recent changes in law, especially in European Union, enforce the decision support systems to explain their decisions to the users. Those changes addresses the risk that models will make the decisions based on the wrong and ambiguous reasons. Lack of explainability limits deep learning applicability in many fields, including medicine. That is why we aim to introduce a comparison framework between supervised and self-supervised models that will show the difference between the model's reasoning process based on the image representations. Additionally, we want to analyze how the model size influences the learned features. To compare supervised and self-supervised representations, we define 5 visual features that play an important role in the human perception system. Those features are as follows: contrast, color, saturation, shape, and texture. In our experiments, we are changing each of those features of the image with different magnitudes and compare the model responses to them. Here on the bottom of the slide, you can see the original image and the same image after different transformations that we are using. When we have trained models, we process by the model the original and transformed image and look into the absolute difference between model predictions. In that way, we can quantify the change between model responses. For example, if we change the texture of the image and the difference between output is large, it means that the texture feature is important for the model. Then When the difference is small, it is not important at all. To assess our framework, we use a dataset from the Panda Challenge. It contains whole slide images of prostate biopsies. We used masks annotated between 3 and 4 Gleason's patterns, and we extract patches of size 512 by 512 pixels. This results in around 363,000 of patches. And here you can see the example of the image and annotations from the dataset. The red part annotates Gleason 5, orange Gleason 4, yellow Gleason 3, and green the benign tissue. Firstly, we show the effectiveness of trained models on the task of predicting Gleason 3 or Gleason 4. We can observe that in most cases, self-supervised training surpasses the supervised one. The results are averaged through fourfold cross-validation process on separate holdout set, and the bold values correspond to statistical significance between the results using Wilcoxon rank tests. Here we present the distribution of differences between the importance of visual characteristic. We present only those which show differences between supervised and self-supervised models. One can observe that self-supervised models put more attention than supervised on the image contrast. Additionally, the supervised methods code information about fine texture characteristic, while self-supervised focuses on more coarse texture properties. Here we present the canonical correlation between models and conclude that models are rather not similar except for the last layers of CBR large tau and CBR tiny, that obtains the highest and the lowest similarity to random weights respectively. To conclude, we observe that self-supervised models are more effective on these tasks than their supervised counterparts. We show that the smaller models can be as effective as deep ones. And we prove that in the case of histology of prostate cancer, self-supervised models are biased toward texture and contrast, while supervised towards the shape. In the future, we plan to extend this framework to be used to compare other architectures and methodologies. We also extend it with other transformations. Additionally, we'll consider other types of medical images to study how general the framework is. Thank you for your attention. In case of any questions, please send an email to given address.